Good evening, everyone. Is my slides visible?
Yes, ma'am. Good evening.
Okay. So today is your problem solving session 8 and I'm your TA Vidushi. So in this class, we will discuss about fluorescence spectroscopy. So what do you understand by fluorescence spectroscopy? Fluorescence spectroscopy, or you can say spectrophotometry, it is a type of electromagnetic spectroscopy which analyzes the fluorescence from a sample. Fluorescence is a phenomena whereby molecule after absorbing radiation emit the radiation of longer wavelength. That is, a compound absorb UV radiation and emit visible light. Suppose like a molecule, you have provided a light, then a molecule in the ground state is excited to the higher energy state, that is excited state, then further relaxes back to the lowest vibration level of the excited state, then it will return back to the ground state. And here the light is emitted, and this is called as fluorescence, or you can say that emission. So basically what happens in fluorescence, where a molecule after absorbing radiation, it will emit the radiation of longer wavelength. Why it is called as longer wavelength? If you will see, the energy is less here corresponding to the energy of absorption. So you know that energy is inversely proportional to wavelength. So if energy is low, then wavelength will be higher. Therefore, the emitted radiation will be of longer wavelength comparative to the absorbed one. Now, what do you understand by the term stock shift? So basically, if you have this graph, this is your absorption graph and this is your emission graph. So the gap between these 2 points is called a stock shift. That is gap between the absorption maximum, the wavelength maximum of absorption to the wavelength maximum of the emission. The difference between them is called as the stock shift. So the best results are obtained from these compounds which shows larger shift. So if you know the value of, suppose here it corresponds to 300 nanometer and here it corresponds to 500 nanometer. So what will be a stock shift? Stock shift will be 500 minus 300 nanometers, that is 200 nanometers. And stock shift we calculate in wave number. So you can convert this value of nanometer to wave number. You know wave number is inversely proportional to wavelength, and wave number are generally in centimeter inverse. So in this manner you can calculate the stock shift. So basically for the stock shift you should know the lambda absorption and lambda emission, and the difference will be the stock shift. So here it's 200 nanometer, and generally the wave number we calculate is in centimeter inverse, and here it's wavelength, so you will convert this into wave number. So the answer will come in centimeter inverse. So that's called a stock shift. And just remember, if there are two values of stock shift, so the best results will be obtained when there are large stock shift. Now what do you understand by the Jablonski diagram? So Jablonski diagram is used in fluorescence spectroscopy to illustrate the excited states of a molecule and the radiative and non-radiative transitions that occur between them. So basically what are radiative and non-radiative transitions? So basically there are two types of transitions. that are radiative and non-radiative. So as the name suggests, what are non-radiative transitions? So non-radiative transitions are those transitions which do not involve any emission of radiations, that is they are radiationless. And generally in internal conversion, intersystem crossing, these are the non-radiative transitions. And what are radiative transitions? Radiative transitions are those transitions which involve some radiations, and it can be fluorescence, it can be phosphorescence. So we will look upon these terms. So if you will see, if you provide some light, then a molecule from a ground state is excited to a high excited state. Suppose from S0 it is excited to S2, or it can be possibility the molecule is excited to S1 also. So it can get excited to any excited state. It can be S1, S2, S3 depending upon the energy we supply. So after reaching the S2, it relaxes back to the lower level of the vibrational state of the excited state, that is S1. So it relaxes back to the S1 state, and from the S1 state, when it goes back to the ground state, that is S0, it emits the light in terms of the fluorescence. So basically what do you understand by fluorescence? The transition from the S1 to S0 state is called as fluorescence. Secondly, if the molecule from the S1 state goes to the triplet state, like from here S1 it goes to the triplet states, so it is called as inter-system crossing. So basically what happens in this, the spin is changed. Now from singlet it goes to triplet, so that is called as inter-system crossing. And if the molecule returns back to the ground state from the triplet state, it is called as phosphorescence. So basically, just to remember, what is the difference between fluorescence and phosphorescence? Yeah, in fluorescence there is no change in the spin, like the molecule will return from the S1 to S0 state, while in phosphorescence there will be a change in the spin, that is the molecule will return from T1 to S0 state. S0 is your ground state. Suppose this is your ground state and this is your excited state. So a molecule will be excited from ground state maybe to first excited state or to the second excited state. From here this molecule relaxes back to the lowest vibration level of the first excited state, and from here the molecule returns back to the ground state and it emits the light called as fluorescence, the form of fluorescence. There is another state that is called triplet state, which have a less energy than the singlet state. If a molecule from S1 goes to a triplet state through inter-system crossing, this transition is called inter-system crossing, ISC. So from here, if this molecule return back to the ground state, then the emission is in form of phosphorescence. So remember that fluorescence and phosphorescence, these both are the radiative transitions. While if you look that in the internal conversion, if a molecule goes from S2 to S1, this is internal conversion, and what happens in internal conversion, the energy is emitted in the form of heat, and this is also a non-radiative transition. While ISC, that is inter-system crossing, it is also a non-radiative transition. also remember in the internal conversion, the energy is emitted in the form of heat through the molecular collisions. Through molecular collisions. Is it clear?
Yes, ma'am.
Okay. And here also you have to remember the time
Ma'am,
scales.
this interconversion is due to the molecular collision, right?
Yes, actually what
That
happens,
intersystem cross.
no, I'm just telling like in the internal conversion, what happen is that the molecule from the S2 goes to the S1 state through internal conversion. And basically what happens in the internal conversion, when the molecule is coming back to S1 state, it will emit the energy in the form of heat. And why this happens? It happens due to the molecular collisions. While in intersystem crossing, the molecules are in the S1 state. And below S1, there is another state of lower energy that is called triplet state. So in the intersystem crossing, the molecule can easily go from S1 to T1 state. And from that T1, it further goes to the S0 state. So the transition from S1 to T1 is the intersystem crossing. And you also know that in intersystem crossing, the spins are different. Like it goes from S like singlet to triplet. And we already discussed in our previous session, like this is a forbidden transition. Is it clear? So as it is a forbidden transition, so it occurs in a slow rate.
Yes, ma'am.
Okay. Also, you have to remember the time scales. Like if you will look upon the absorption. So first process is the absorption. So the time scale is 10 raised to a minus 15 seconds. And what is this vibration relaxation? It's that when a molecule in the highest singular state, it relaxes back vibrationally to the lowest excited state or the lowest vibrational state or the first excited state. It's called the vibrational relaxation. And here the time scale is 10 raised to minus 14 to 10 raised to minus 11 seconds. For the fluorescence, you should remember it's 10 raised to a minus 9 to 10 raised to a minus 7 seconds. And for phosphorescence, it is 10 raised to a minus 3 to 10 raised to a 2 seconds. So this all you have to remember. Also, what do you understand by the term quenching as it is depicted here? So what is quenching? Quenching is like when there is decrease in the fluorescence intensity. It is called as quenching. Quenching we will discuss in detail in further slides also. It is decrease in the fluorescence intensity. So is it clear? Just remember if a molecule is in ground state and here the excited state, or you can say if it is S1 state. So molecule from ground state excited to the highest state, and if the emission is from the higher excited state to ground state, then it is fluorescence. If it occurs from triplet to ground state, then it is phosphorescence. And also the vibration levels are same in ground state as well as in the excited states. And that is the energy gap between these vibrations levels are also the same, like in the HOMO or the LUMO, or you can see the ground state and excited state, the energy gap between these vibrational levels, like you see these energy gaps are same. Now what do you understand by quantum yield? So basically quantum yield is P unit to 5, so it is number of photons emitted to number of photons absorbed. So you know that in emission, like what are the relative transitions? It is fluorescence. So it is equals to the rate constant of the fluorescence, like the emissive rate, and divided by photon absorbed. So it can be radiative plus non-radiative. So it is rate or emissive rate plus rate of the non-emissive, that is non-fluorescence. So in that non-fluorescent or non-radiative decay, it can be internal conversion, it can be intersystem crossing, or others can come here. So just remember, quantum yield is equals to number of photons emitted to number of photons absorbed. Secondly, what do you understand by fluorescence lifetime? It is the time that a molecule spent in the excited state before coming back to the ground state. So the time that a molecule spent in the excited state is called as fluorescence lifetime, and it is denoted by tau, and it is equals to the 1 by emissive rate, that is K fluoro. So basically, if a molecule is in ground state here and here it's excited state, so when it is excited to the higher energy state, so it may return back through two transitions. It can be radiative transition or it can be non-radiative transitions. So just remember what's quantum yield. Quantum yield is equals to the rate of the emissive rate or the rate of the fluorescence divided by emissive rate plus non-radiative rate. So this formula you have to remember. And also just remember what's the value of non-radiative. Here it can be internal conversion, it is addition of internal conversion, intersystem crossing, and others also. So next is quenching. Basically, what do you understand by quenching? Quenching means decrease in the fluorescence intensity. Quenching refers to the any process that reduces the fluorescence intensity of a given substance, and it may occur due to various factors such as pH, concentration, temperature, viscosity, due to presence of oxygen, heavy metals, or some specific chemical substances. So for a reference, this is an image. It's in quenching of quinine fluorescence in presence of chloride ions. So when chloride ions were added in quinine, its fluorescence get quenched. So here chloride ions act as a quencher. So now if you look upon the quenching, it can be of four types. It can be collisional quenching, it can be chemical quenching, it can be static quenching, or concentration quenching. So what do you understand by collisional quenching? The quenching are of four types: static, collisional, chemical, and concentration. So what is collisional quenching?
At excited state, the atoms or molecules collide with each other and energy transfer takes place
Okay,
through collision.
yeah. So basically what happens in the collision quenching, it occurs by the interaction of the quencher molecule with the excited molecule of fluorescence molecule, the fluorescent molecule. So the interaction between the quencher and the excited state molecule of our fluorescent molecule is called as the collisional quenching. And what do you understand by the static quenching? What do you understand by static quenching?
At ground state,
What's ground state? Yeah, it occurs at the ground state of the fluorescent molecule. Then what next? So basically there is a complex formation. So what happens in static quenching is that it occurs in the ground state of the fluorescing molecule. So these ground state fluorescent molecules, suppose I am denoting by F star. So there is a complex formation with the quencher and the F star in the ground state. So that is called as static quenching. Is it clear? So now you know the difference between collisional quenching and static quenching. So in collisional quenching, the interaction is between the excited molecule of the fluorescing substance with the quencher. While in the static quenching, there is a complex formation in the ground state of the fluorescent molecule with the quencher. So it occurs in the ground state, it occurs in the excited state. So now what do you understand by the concentration quenching? Concentration quenching. So it is also called as self quenching. Basically, what as the name suggests, what's concentration quenching? If you increase the concentration, then the fluorescence intensity gets decreased. Please mute yourself. So what's concentration quenching? It is called as self quenching. And what happens in concentration quenching is that if we increase the concentration of the analyte, then the fluorescence intensity get decreased. So that is called as concentration quenching. Now what is chemical quenching? Why does chemical quenching occurs? It may occur due to change in the pH, presence of oxygen molecule, or heavier metals. So due to this, chemical quenching occurs. So is it clear? So basically there are four types of quenching: collisional, static, concentration, and chemical quenching. So what happens in the collisional quenching is that the quenching occurs due to the interaction of the molecule in the excited state, like what's the molecule, the fluorescent molecule, with the quencher. And in static quenching, there is a complex formation with a ground state molecule of the fluorescent substance and the quencher. While in concentration quenching, it is also called as self quenching. If we increase the concentration, then fluorescent intensity get decreased. So it is a self quenching. While chemical quenching is that due to pH it may occur, or due to the presence of oxygen or heavy metals. As an example, you may remember quinine is a fluorescent molecule. It gets quenched in the presence of chloride ions. So here chloride ions will act as a quencher. See here, fluorescence get quenched. Is it clear? Like, is it clear to everyone? Like, what is quantum yield, what is
Yes, ma'am.
lifetime? Yes. Also, like, there is another term that is called as intrinsic lifetime. So, do you know what is that term? What is intrinsic lifetime? Or you can say natural lifetime. When you have we have discussed fluorescence lifetime, it is the time that the molecule spent in the excited state before coming back to the ground state. And here it is not by tau, it's 1 by k fluoro, the emissive rate of fluorophore. So what do you mean by intrinsic or like natural lifetime? Basically, if you what's natural or intrinsic lifetime, it is same as that only, but it occurs in the absence of the non-radiative transition. Non-radiative. So basically, it is the lifetime or the time spent by a molecule in the excited state in the absence of non-radiative. So here it is also 20 by tau. It will be equal to 1 by kr. Also, if I will ask like generally what's the lifetime of excited state, what's the lifetime of excited state? So it will be equal by 1 by or instead of this you may write this. This is one the same thing, emissive rate of the fluorophore plus non-radiative one. That's the lifetime of the excited state. And if you look upon the fluorescence lifetime, it will be tau f equals to 1 by k fluoro. Is it clear? And also remember, if like there is some aromatic molecules that contains NO2 group, in that case the non-radiative transition will be higher. So they will have a large KNR value if an aromatic molecules contain NO2 group. Now there is another energy transfer that is called as Foster resonance energy transfer. Here also the molecule, the fluorescence can be quenched or it can be decreased. Why? Because there is some energy transfer from one molecule to the another. So it is Foster resonance energy transfer. So what is this? It is denoted by FRET. It is a transfer of the excitation energy from one chromophore to another chromophore. And there is some conditions or some prerequisites that must be met so that we can achieve the FRET. So what are these? That the emission of the donor should overlap with the acceptor's absorption. So basically there is a spectral overlap in this case. So sorry, if I will just one example. This is your donor, this is your acceptor. So this kind of overlap. This is spectral overlap. So this is a prerequisite of FRAT, that is the emission of the donor. Suppose this is donor molecule and this is acceptor molecule. So you are exciting the donor molecule and that donor molecule is emitting some light. So this emitted light will be taken by the acceptor molecule and further the acceptor will emit the light. So the donor's emission should overlap with the acceptor's absorption for a perfect FRAT. Also there is another condition for a FRAT, that is the orientation of the dipole should be optimum of dipole. Like the best FRAT is achieved when the orientation is parallel. Also, the distance also of the donor and the acceptor also matters. So these are some factors that should be met to achieve FRAT. So just remember, for FRAT, the emission of the donor should overlap with the acceptor's absorption. That is, there is a spectral overlap. Second, the distance between the donor and acceptor. Third, the orientation of the dipole should be optimum, or you can say should be parallel. So basically, if you will see, this is a donor molecule, and it is a donor molecule in the excited state. It is acceptor, and here is the acceptor in the excited state. So donor molecule, after excited to the higher excited state, it transfers the energy to the acceptor, and then acceptor goes to the higher state. So this is the FRAT. And also remember, the efficiency of the FRAT, it corresponds to 1 by R6 dependence. And FRAT can occur only within the nanometer range. Is it clear? Is it clear? Like, what is FRAT?
Can you repeat that distance between the donor and that
Yeah,
the transition of donor to acceptor?
like the orientation matters. Like how the molecules are oriented, how the dipoles of the donor and acceptor are oriented, that matters for a FRAT. So the orientation can be optimum. It should be optimum for a FRAT. Suppose like the best orientation is when the donor and the acceptor molecules, the dipole are parallel to each other. Secondly, donor's emission and acceptor's absorption, that is a spectral overlap, should be there. Third, the distance between the donor and acceptor should be less than 10 nanometers, so it should be in nanometer range, like distance. Also, like if you'll see energy transfer efficiency, it is denoted by R06 by R06 plus R6. And what's R0 here? R0 is the Foster radius. So just remember, efficiency of the FRAT corresponds to 1 by R6 dependence. So here in this graph, it is plotted between transfer efficiency and R0. R0 is the Foster radius. So it corresponds to 1 by R6. Is it clear?
Yes.
Okay. Now just tell me, like, what do you understand by some, like some there are, what is the basic difference between absorption and emission? Like we already discussed in the Jablonski diagram. So how you will compare, like what's the difference between absorption and emission? So basically absorption is the instantaneous, is instant, and emission takes time. It occurs over long period of time. So as there is a long period of time, so here your fluorophore or your compound can interact with the solid molecules. So basically what happens is that molecular dynamics, you can see molecular dynamics, as there is long period of time. Emission is what? Fluorescence. So in this, there may be interaction with other solid molecules like dissolved oxygen also. While in absorption there is no such interaction because it is very instantaneous. Like the absorption, the time scale for absorption is in picoseconds or femtoseconds, while emission is generally occur 10 nanoseconds, within 10 nanoseconds. Is it clear?
Yes, ma'am.
Okay. And like before solving some questions, I will just tell you about some terms like what are the characteristics of like how you will see a molecule is a fluorophore, or like how a molecule will show fluorescence. So what are the properties for a molecule to be fluorescent? It should be rigid. And what else for a molecule to be a fluorophore? Like if I will give you a structure of a compound, so how you will tell like whether this molecule is a fluorophore or not, apart from rigidity. It should have delocalized electrons. And what else? Kartike, Arun, Rohit. So how you will say that a molecule is a fluorophore? It should be rigid. There should be delocalized electrons. There should be a good overlap in the wave functions of the excited state and the ground state. Show intense absorption band. Is it clear? Short
Yes,
excited
ma'am.
lifetime. So if a molecule show these characteristics, so you can say the molecule is a fluorophore. So a fluorophore, it should be rigid. It should have delocalized electron, good overlap, intense absorption band, and short excited lifetime. So now we will solve some questions.
Hello, ma'am. This is Vasu.
Yes.
Ma'am, we are not means uh, in the previous assignments what we are writing. That problems are not discussed in anywhere, madam. I mean, not the current assignment. Previous assignments are not discussed anywhere, and also previous assignments are not solved. Solved questions also not displaying in the NTPL portal, madam.
Like I can't. Can you repeat your question actually?
Madam, previous already some 7 assignments are completed.
Yes.
But we have so many questions on that doubts on the questions, ma'am. But once we are repeated in the those questions, we have discussion on the those assignments will be helpful to us for the exams, madam.
Yes. Oh,
But it's not happening. So please incorporate those questions also.
but actually some of the questions I am already explaining in the sessions.
No, madam. I am regularly attending the sessions, but we are not means some questions. Okay, but remaining questions what we are missed in the discussion.
So
So
you're telling me
means
like to repeat
as
that
overall
we
we are getting very low marks. Hello.
okay. So you're telling me to
So
repeat. Yeah, speak.
explanation key also not releasing in the only for this course only not releasing, madam. Other courses they are keeping in the NPTEL portal.
That
Uh,
actually that answer key you're telling me, na? That's like for
yes,
the
ma'am.
assignments. Okay. Actually, that you have to maybe write some mail to that instructor. He will upload that.
Ma'am, ma'am, I'm written the mail, but no response from that side, ma'am. Please, uh,
Okay.
from your side also, please keep the reminder.
Like if you have any doubt in any assignment question, you may ask in the chat box. I will just solve it now. But actually,
Okay, ma'am.
yeah. Actually, that answer key you are asking, that only instructor can add on that portal.
Okay, okay, ma'am.
Yes. But anyways, like the doubt session are helping you to solve the assignments.
Not all the assignment questions. I mean, only 10% it's covering, madam. Remaining 90%, we don't. These problem solving sessions are not helpful to address those questions, assignment questions.
Okay, so what are the questions that you want, like that are not addressed? Like if I could remember in the starting 2 3 assignments, like not directly, indirectly, every question was solved in the session.
Okay, ma'am. I will prepare and I will ask in the end of the session.
Yeah. Just ask me, like if you're facing any difficulty in the previous assignments, then you may ask.
Okay, ma'am. Okay.
And maybe in the last, like we will have I think 6 more sessions. So maybe in the last session I will cover all the assignments questions.
Also assignments questions. Okay, ma'am. That helpful. That I also want to ask the same, madam. That helps us a lot.
That I will
That helps a lot
actually I
to
can't upload.
present.
Actually, I can't upload the same questions. I can
No
only
problem, madam.
solve
Just
the previous.
briefing on the concept.
Yeah,
Yes.
because like in the previous also, like we were discussing about some, I think the spin questions one,
Ah,
like with the ground
all
state
those
terms. So
covered.
that
Ma'am.
questions were already
Ground
covered.
state. Yes, ma'am.
Yes, because we will have I think one more session extra. So in that I will discuss all the questions that I have not discussed in the problem session. Because at that time your assignment will also be
Ah,
over.
yes, ma'am. Previous assignments only I am asking you.
That I will cover. But now I
Okay.
can't, like directly I can't cover the same question, like the current
No,
assignment.
madam. I am not
Yes,
asking the current
yes.
present assignment 8, week 8, previous
Okay,
assignments only.
okay. So the question is fluorescence quantum yield and the fluorescence lifetime of a molecule are 0.4 and 5 into 10 to minus 9 second respectively. If the fluorescence decay rate constant is y into 10 to 7 second inverse, what's the value of y? So how you will solve it? Like fluorescence quantum yield is given is 0.4 and fluorescence lifetime is also given, it's 5 into 10 to minus 9. So quantum yield is 0.4 and the fluorescence lifetime is 5 into 10 to minus 9. So you have to calculate the fluorescence decay rate. And if it is y into 10 to 7, so what will the value of y? So now we have discussed a formula for the quantum yield. So what's the formula of quantum yield?
Number of photon emitted by number of photon absorbed.
Yeah, or
Rate of fluoro by
yeah, or if you can simple say, it is the emissive rate of the fluorophore divided by the emissive rate of fluorophore plus the rate of non-emissive decay, that is non-radiative. So this is also quantum yield, correct?
yes, ma'am.
And what's fluorescence lifetime? It is 1 divided by kf. So if you will substitute, like equate these two, then you get a direct relation between the fluorescence decay rate, that it is equal to the quantum yield divided by fluorescence lifetime. So quantum yield is 0.4 and your fluorescence lifetime is 5 into 10 raised to minus 9 seconds. So the fluorescence decay rate will be equal to the 8 into 10 raised to 7 second inverse. So this is your y value. So y is 8 here. Is it clear? Is it clear?
Yes, ma'am.
So now solve the second question. The quantum yield and lifetime of a dye were measured to be 0.43 and 2.6 nanoseconds respectively. What is the natural lifetime? The quantum yield is 0.43 and lifetime is 2.6 nanoseconds. So what is the natural lifetime?
Only non fluorescence will be not there. Only fluorescence will be there.
That's
Absence
natural
of
lifetime.
non-radiation.
That is natural lifetime. You're defining. So what will the value? You have to substitute the value quantum in lifetime not to calculate it. So just tell me the value. Is it clear that natural lifetime will be 1 upon rate of the fluorescent one, not of the non-radiative one? Is it? This is clear. The natural lifetime will be equal to 1 by kf. So how you will solve it? Like now you already know all formulas of quantum yield and lifetime. So basically, what's natural lifetime? It will be equal to the lifetime of a dye, lifetime divided by the quantum yield. So lifetime is 2.6, quantum yield is 0.43. So that will give you a natural lifetime. So after solving it, it will come out to be 6 nanoseconds. So like how the formula is lifetime by quantum yield? Like in the previous question, we solve also like quantum yield is equals to emissive rate of the fluorophore divided by emissive rate of fluorophore plus non-emissive rate, and lifetime 1 divided by fluorescence rate and non-fluorescent rate. So on substituting these two or equating these two, you will get this formula. So the natural lifetime will be 2.6 divided by 0.43, that corresponds to 6 nanoseconds. Now next question, which among the following class of compound shows intense fluorescence? Compounds having aromatic functional group, compounds having aliphatic carbonyl structures, compounds having alicyclic carbonyl structures, compounds having conjugated double bond. Like intense fluorescence will be visible in case of
Conjugated.
Aromatic.
aromatic functional group.
Aromatic functional group.
Yeah, it will be aromatic functional group. Maybe like in the next class or the next session, I will, like today is your I think 8th session, na? So maybe in the next session I will discuss the assignment questions up to 7 assignments. Like all the 7 assignments, like the question which I have not discussed here, I will discuss in the next session up to like 8th maybe, na? Because that time it will
Oh,
be 9th.
okay.
Yeah. So here the answer will be compounds having aromatic functional group. Now the next question. Fluorescence efficiency in most molecules increases with increasing temperature, increasing solvent viscosity, increasing quencher concentration, or none of the above.
Increasing quencher concentration.
If you will increase the quench, then fluorescence will be quenched. The fluorescence intensity will decrease. Like we discussed now, like if we will add chloride ions in case of quinine, then the
Increasing
as quinine.
Yes,
temperature.
ma'am.
So the question is fluorescence efficiency will increase with. You have to increase the intensity of the fluorescence. So what will be the answer?
Increasing solvent
Increasing temperature.
viscosity.
It will be increasing
Okay.
temperature. So with increasing temperature, the fluorescence intensity will increase. Now next question. The energy of the emitted radiation in stopped fluorescence is greater than excited radiation, lower than excited radiation, equal to excited radiation, sometimes greater and sometimes lower depending on the nature of the molecule.
Lower.
Lower than the excited radiation. So basically what happened is
Weak
that,
or low.
see what's excited radiation. Basically, suppose you have a molecule in ground state and here it's excited state. So molecule goes to the high excited state when you supply some light or energy. Then from here it vibrationally relaxes back to the lowest vibrational level of the excited state. Like this is absorption. So from here it emits back or returns back to the ground state by the emission of the light in terms of fluorescence. So now if you compare absorption and emission fluorescence, so the energy is less in case of fluorescence. Is it clear? So the lambda absorption will be lower than lambda emission. So lambda emission will be higher. So they are asking energy of the emitted radiation. The energy of the fluorescence, it is less than the energy of the excitation. Is it clear now? Like how it is less? See, if a molecule you are
Yes,
absorb,
ma'am.
if a molecule you are if a molecule is absorbing a light and it is excited to a higher state, then it further vibrationally relaxes back to the lowest vibrational level of the first excited state, then it further returns back to the ground state. So here, if you'll see, here the energy is high in absorption, but in fluorescence it is less. So the answer will be lower than the excitation radiation. Now the next question is, eosine is more rigid than phenolphthalein. Which of the two substances does not fluoresce? Eosine, phenolphthalein? It can't be predicted.
Phenolphthalein.
Yes. As you know, like we discussed, what are the characteristics of fluorophore? That it should be rigid. So basically, eosine is more rigid. That means it is fluorescent. That's why answer will be phenolphthalein. Answer will be phenolphthalein. Now next, the fluorescence intensity increases with all except rigidity, planarity, number of rings, dissolve oxygen.
Dissolved oxygen.
Correct. As we discussed, like rigidity increases the fluorescence, planarity will also increase, and how number of rings, like delocalized electrons, will increase. So fluorescence intensity also increases. So only in case of dissolved oxygen, the fluorescence will not increase. Because here what will happen that
Quenching.
quenching will occur. Why? Like after intersystem crossing can happen, like from S1 to T1, and then after T1, instead of going from S1 to S0, it will goes to S1 to T1. So that's why. And you know, from T1 to S0, it's phosphorescence. Now what is the average, when the average lifetime of the excited electron is in order of 10 raised to minus 12 second, it mainly results in fluorescence, phosphorescence, vibrational relaxation, and all of the above. So time scale is 10 raised to minus 12 seconds. So it is fluorescence, phosphorescence, or vibration relaxation.
Vibrational relaxation.
Yeah, it will be vibrational relaxation. Now next, the selectivity and the sensitivity of fluorescence spectroscopy is higher than that of absorption spectroscopy because fluorescent substances have different lambda max of excitation and emission. Rigid molecules can only fluoresce. Fluorescence intensity depends on the intensity of the incident radiation. Every molecule that absorbs in UV can cause fluorescence.
Option D.
Option B. They're asking why fluorescence is more sensitive than absorption.
Option
This
A.
this is true that rigid molecules increases the fluorescence. But how sensitivity of fluorescence is higher? Why? Because in case of UV, every molecule that absorbs UV can show fluorescence. So that's why fluorescence is much more sensitive than UV. So option D will be the right answer, not A or B. Now next question. Phosphorescence mainly results from internal conversion, vibrational relaxation, intersystem crossing, or all of the above.
Option C.
Intersystem crossing.
Yeah, through intersystem crossing. So from S1 to T1, it's intersystem crossing, and in intersystem crossing there is change in the spin.
Previous question answer is D, ma'am.
Yeah, it's D.
Okay.
That is, every molecule that absorbs in UV region can show fluorescence. Now next question. The quantum yields of various deactivation processes in small organic molecules measured at 77 Kelvin in a glass matrix. So you have been provided with the quantum yields of fluorescence, and what's ST, like singlet to triplets. It's phosphorescence. So it is quantum yield of fluorescence, and this is a quantum yield of phosphorescence, and delta E, del E. So del E is your energy gap. And this is a quantum yield of phosphorescence. This is a quantum yield of fluorescence. So naphthalene, anthracene, pyrene, tetracene, pentacene. So for these, you have provided these values. And the question is, when examining the data above suggests that why it is likely why the quantum yields of both fluorescence and singlet to triplet intersystem crossing decrease with increase in molecular size, as like downstairs, like as in down moving from naphthalene to pentacene, the molecular size is increasing. So why is it like that? The fluorescence and intersystem crossing, a single to triplet, that is phosphorescence, the quantum yield is decreasing. So if you will look upon early naphthalene, it was 0.20, but in pentacene it is 0.1, so it is decreasing. So what would be the reason for that?
Because energy gap reduces simultaneously.
Energy gap is also reducing. So what's the reason? So basically, you have to take two factors in mind. The first one is rigidity, and second one is the homo-LUMO energy gap. So now just tell me, you can take your time. Just tell me, why is it like that in naphthalene the quantum yields are high while in pentacene it is low? Like now you know that in naphthalene the energy gap is highest, like it's 385. The energy gap between the HOMO and LUMO is highest in naphthalene.
Delocalized electron increases.
Delocalized electrons increases.
Conjugation increases. So energy graph decreasing.
It is clear that energy gap is decreasing. But why quantum yield is decreasing? Like for both fluorescence and the phosphorescence. Like both for the radiative transition, the quantum yield is decreasing. So basically, HOMO and LUMO energy gap is highest in naphthalene. So if I just take an example of naphthalene. So this is a naphthalene. So this is your naphthalene molecule. So basically what happens is that the energy gap, that is del E, is highest here. So basically the overlap of the wave function of the excited state and the ground state will be smaller. Why? Because the energy gap is higher here. So as the energy gap is higher, therefore the overlap of the wave function of the ground state and the excited state will be less. And because of that, the rate of internal conversion will increase. Like like there are wave function of the excited states, or like this is a ground state and excited state. So these wave functions, due to the large energy gap, the overlap is not good here in the excited state and the ground state. So because of that, the internal conversion rate will increase. Therefore, it is like that. Therefore, the quantum yield is higher. So quantum internal conversion will be less. The quantum yield is higher. So like if you take pentacene, in pentacene what happens is that there are 5 aromatic rings now. In this the homo-LUMO gap is minimum. So there is a better overlap of the excited state and the ground state, and due to better overlap, internal conversion will be more, and when internal conversion is more, the quantum yield will be less. Is it clear?
Yes, ma'am.
So here it happens why? Because intersystem crossing is less in case of naphthalene. That's why naphthalene quantum yield are higher. If you compare pentacene, the internal conversion rate is higher. Why higher? Because there is better overlap of the wave function of the ground state and the excited state, as energy gap is less here. Now next question, which will have high quantum efficiency, fluorine or biphenyl? Just look at the structures. This is structure of fluorine and this is structure of biphenyl. So which will have a higher quantum efficiency?
Fluorine.
Why fluorine?
It is rigid.
Yeah, correct. It is rigid. So higher quantum efficiency will be in fluorine. Why? Because it is rigid. Now here, if you look upon biphenyl, there is one single bond here. So fluorine will be the answer. Next question is high relative intensity of fluorescence. Like if you compare fluorobenzene and bromobenzene, which will have high intensity of fluorescence?
Fluoro. Fluoro.
Fluorine. Why fluorine?
more electronegative and less molecular weight. So it will not decrease the fluorescent intensity as so much as compared to chlorine and bromine.
Actually, what happened is that if in a molecule there are these molecules, fluorine, fluorine, bromine, so these are considered as a heavy atom. So because of heavy atoms, there is intersystem crossing due to spin orbit coupling. Therefore, the transition is from S1 to T1. Otherwise, it should be S1 to S0 for the fluorescence. But due to this presence of these fluorine, chlorine, and bromine, they are heavy atoms, and due to that, the intersystem crossing is more fissile. Therefore, the fluorescence intensity decreases in these three. But if we will compare these three, so intersystem crossing rate is higher if the molar mass or the size of the molecule increases. If the size of the molecule increases. So you know na, in the periodic table it's fluorine, then comes chlorine, then comes bromine. And down the group size increases. So in bromine, the intersystem crossing will be more. Therefore, intensity of fluorescence will be lower in bromine. So the answer will be fluorine. So high relative intensity of fluorescence will be in fluorine. Is it clear?
Yes, ma'am.
So just remember, like for a molecule to be fluorescent, it should be rigid, delocalized electrons, short excited lifetime, and it should avoid intersystem crossing. Because if it is intersystem crossing, then there will be phosphorescence instead of fluorescence. So now, and if you compare these three benzenes like fluorobenzene, chlorobenzene, and bromobenzene, in all these molecules due to heavy atoms, the fluorescence intensity will decrease. But in case of bromine, as the size is higher in bromine, therefore the intersystem crossing will be more in bromine. Therefore, the fluorescence will be very less. So the high intensity will be of fluorescence will be in fluorobenzene. Now, next question. 5,10 dihydro Indene 2,1A indene and trans-stilbene are similar in structure like these two, but have a very different fluorescence quantum yield of 0.05 and 1 respectively. However, for trans-stilbene, this increases to 0.75 at 77 Kelvin. Suggest a reason for difference in quantum yield of two molecules or difference of the quantum yields of the two temperatures. So why it is like that? If you'll see, the structures are slightly similar, but quantum yields are different in the room temperature as well as at 77 Kelvin. So why it is so?
One is rigidity, ma'am.
Rigidity, okay,
First one is more rigid.
correct. First one is more rigid. So basically, what happen is that, like, if you will see the structure of the steel beam, this one, steel beam has a double bond. So here easily you can do rotation. So the rotation of the double bond can be occur in steel beam. So because of that, there will be internal conversions. There will be efficient internal conversion here. efficient internal conversion. Whereas, like, if you will see Indian, there is an additional structure here, this one. So because of that, it is rigid and there will be no rotation possible here. Therefore, quantum yield is higher for this molecule than this. Is it clear? Like for the steel beam, there is a double bond, so you can easily rotate around this bond. And because of rotation, there will be internal conversion efficient here, and that's why quantum will be less. Like in the previous question after solving, we know that internal conversion is inversely to quantum yield. So like here, the structure is rigid, like this additional structure here. Because of that, there is no rotation possible. That's why it is more rigid. Therefore, internal conversion will be less and quantum yield will be more. So quantum yield of this is higher.
0.05 is for which, ma'am? Quantum U.
Like 0.05 is for indium and trans-Kelvin it's 1. But it's increasing now, like they're asking why it is increasing for trans-Kelvin. Like from 0. So from like the first one is of the trans-Kelvin and second one is for the indium.
Yes, ma'am. First
Yeah,
one is for
yeah, it's written wrong.
trans-Kelvin. Second is
It's written wrong. The
Indian has
first,
a higher
the
quantum
first
yield
one,
than the
yeah,
trans-Kelvin.
it's written wrong actually.
Okay, ma'am.
And so what affects like trans-Kelvin, if it was 1, now it further increases to, sorry, it's 0.05 and further increases to 0.75 at 77 Kelvin. So why is it like in trans-Kelvin? The quantum edge is increased to 0.05 to 0.75 at 77 Kelvin. So what happened is that 77 Kelvin means when you cool it, the rotations are frozen. So the molecule can't rotate. Therefore,
Rigidity increases as the temperature increases and molecule become more rigid and unable to move. Like
correct. So what happened is that at 77 Kelvin means you are freezing the molecule. You're cooling the molecule. So basically at that there will be molecules will be restricted. There will be no rotation possible around the double bond because it will be in a frozen state. That's why the quantum will be increased to 0.75. Because of that, internal conversion will be less. Is it clear?
Yes, ma'am.
Now explain why the absorption and emission spectra of a chromophore appear as mirror images of each other. Like why is it like the absorption and the emission spectra are the mirror images? Why? This can be explained by some rule that why the absorption and emission spectra are mirror images of each other.
Jablonski diagram.
No, Jablonski diagram is not a tool. Just a diagram that represents various transitions, radiative and non-radiative. So you heard of Kasha rule. So why like these molecule absorption and emission factor mirror images? Suppose if a molecule is in ground state and it is in excited state, and these are different vibrational levels of the same excited state, and same goes with ground state. So if a molecule goes to the excited state, so it may came or it may return back to any vibrational level of the ground state. Secondly, the spacing of the vibration levels in the ground state and the excited states are the same. Like as a consequence of these two, you see a mirror image in case of absorption of the emission spectra. Is it clear?
Ma'am, please repeat one.
Okay. So basically what happens if a molecule is in ground state, there are various vibrational levels associated with ground state. And similarly, if you look upon excited state, there are also various vibrational levels that are associated with the same excited state. So if a molecule goes from a ground state to excited state, it may return back to any vibration level of the ground state. Like it may return anywhere. Is it clear that a molecule from the excited state can return back to any vibrational level of the ground state? Secondly, the spacing, like the spacing between the vibrational level of the ground state and the spacing between the vibration level of the excited state, they are exactly the same. And as a consequence of these two, the molecule or the absorption emission spectra are the mirror images. Is it clear? Like now this is absorption, and like this is absorption, this is emission. Molecules are going to excited state and returning back to ground state, but they can return to any of the vibrational level of the ground state, like here also, anywhere. Secondly, spacing is same, like the spacing between vibration levels, like these vibration levels, these, the spacing is same, the distance between them is same. Therefore, as a consequence of that, you will see an exact mirror image of the absorption as well as the emission spectra. Now it is clear?
Yes, ma'am.
Okay. Now second question. Why does the emission always occur at longer wavelength than the absorption of a dye molecule? This we already discussed. Why is it like the emission always occur at longer wavelength than the absorption of a dye molecule?
Because energy decreases.
More energy required in case of absorption and less energy is required in case of.
More energy is required in case of absorption, correct. But what's that?
There is energy loss during emission.
That, like whatever you are telling that energy of the absorption is higher, that is correct. But there is a term, no, like we discussed, it's called stock shift. So the reason you can say it's stock shift. So the reason you can say it's due to stock shift. And like here, suppose a molecule These are the energy level. So you are providing some light and the molecule is getting excited to the higher energy excited state. Then what happens is that this is your absorption. So from here the molecule relaxes back to the lower vibrational level of the excited state, and after that the molecule returns to the ground state by emission, by fluorescence. So this is your emission. So what happens is that the energy of the absorption is more than the energy of the emission. Therefore, the wavelength of absorption is less than wavelength of emission. So that's why emission always occur at longer wavelength. Is it clear? Is it clear?
Yes, ma'am.
Yes, ma'am.
Now let's solve this question. A donor D with a unquenched lifetime of 5 nanoseconds was found to have a steady state emission intensity of 20.5 in free solution. Free solution means without the quencher, and 4.1 when the in presence of quencher. Q. Assuming the Foster rate distance is 50 Armstrong, determine the transfer efficiency, the lifetime of the donor in the presence of a quencher, the equilibrium separation of donor and the quencher, the rate constant for the energy transfer. So first calculate the energy transfer efficiency. So what's given? That the unquenched lifetime is given, and in presence of quencher it is also given, and in free solution it is given. So now just tell me what will be the transfer efficiency. E, the first part. Like intensity in presence of quencher. Like intensity of donor in presence of quencher is given. It's 4.1. Intensity, like see, in free solution. Free solution means basically without the quencher. ID, intensity of donor, it's 20.5. And unquenched lifetime, it's 5 nanoseconds. So what will be the transfer efficiency E? Anyone? So which formula we will use to solve transfer efficiency one?
0.8.
0.8, correct. So what's the formula that you used?
E is equal to 1 minus I dq upon I dA.
Correct. So energy transfer efficiency is equals to 1 minus intensity of the donor in presence of quencher divided by intensity in the presence of donor. So it is given 4.1 and it is given intensity of the donor is given 20.5. So when you will solve it, the value it turns out to be 0.8. Now tell me what will be the lifetime of donor in presence of the quencher Q. So how you calculate the lifetime of the donor in presence of quencher? You know this formula like energy. There is two formulas of energy like one with intensity, one with lifetime also. Like instead of intensity is lifetime. Lifetime with donor and quencher and with donor only. So now in the question, unquenched lifetime is already given. Unquenched means tau d
without quencher.
without quencher. That is of only donor. So now E value it's 0.8. The lifetime of donor in presence of quench, that is tau dq, you have to calculate, and tau d it's known, it's 5. So what will the value of tau dq after solving? It will be
6 nanoseconds.
you can calculate, like after solving you can easily calculate, just you have to put the value. So value will be also in nanoseconds. Now calculate the equilibrium separation of d and q. How you will solve it? Equilibrium separation of donor and the quencher. This question, equilibrium separation of donor and quencher. Now you know this formula. This is this R, the small r is equilibrium separation of donor and quencher. This you have to calculate. Now you know the formula of E, like the value of E also. It was transfer efficiency. It was 0.8. R naught is the posted radius. That is 50 Armstrong. It's given. So just tell me after solving it what will the value of R. Like you have to only substitute the value. You know E is 0.8. R naught is given 50 Armstrong. So you just have to calculate the equilibrium separation. This R.
10.
What?
10, ma'am.
Please repeat.
12.5, ma'am.
12.5.
Yes, ma'am.
No, it's wrong.
1.22 into 10 raised to minus 12.
It's wrong. Maybe you all are doing some calculation error. It will be 38.2 Armstrong. Now tell me what will the rate constant for energy transfer? So what will the value of rate constant? It's equals to 1 by lifetime of donor So from this equation you can calculate the rate constant for the energy transfer. This all value you know. Just tell me what will the value of the rate constant. So, no, rate constant for the energy transfer.
.26.
1.005.
Wrong. It's 8 into 10 raised to 8. I don't know why, like, so there's some error in the calculation. It's 8 into 10 raised to 8. So, what we have discussed in today's session, like, what do you understand by fluorescence spectroscopy? Fluorescence is a phenomena in which a molecule, after absorbing the radiation, will emit the radiation of longer wavelength. That is, emission will be of higher wavelength. Why it will be of higher wavelength? Because energy corresponding of the emission will be lesser. Therefore, it will be longer wavelength. Then, if you will provide it with a graph, and it's suppose like if you take this graph, so this is corresponds to the absorption. Like, see, here it is excitation, that is absorption, and here it is emission, the green one, that is fluorescence. So if you see that the blue corresponds to the excitation, the wavelength is approx 450 here, and for the emission it's roughly 550, suppose. So now you have been asked, like, what is Stokes shift? So what you will say, Stokes shift is the difference between the lambda absorption and lambda emission. So it will be 550 minus 450, and these are in nanometers. So it is, Stokes shift is 100 nanometer, and generally you represent Stokes shift not in wavelength, in wave number. So just convert this value into wave number. This is also fine, but if the answer is, like in the question it is asked in wave number, so convert the centimeter into the wave number, and the unit will be centimeter inverse. As you know, wave number is mu bar, it's 1 by wavelength. And we also discussed, like, the molecules that have large shift give best results. Then we discussed about Jablonski diagram. It tells about how a molecule, or like how the excited state molecules behave, like what are the transitions involved, radiative, whether it's radiative transition or non-radiative transition. Then we discussed, like, in radiative transitions there are two types basically, fluorescence and phosphorescence. And what's the basic difference between these two? In fluorescence, the transition is from the singlet to, like, S1 to S0, that is, there is no change in the spin. That is fluorescence. And what is phosphorescence? It is the transition from the singlet to a triplet state. So see, there will be a change in spin in case of phosphorescence. Secondly, we discuss what are non-radiative transitions. So non-radiative transitions are those which do not involve any radiations, and we talk about internal conversion, like from S2 to S1, and here energy is lost in the form of heat due to molecular collisions. Then we discussed about intersystem crossing, the transition from the just a sec. Intersystem crossing is singlet to triplet, and phosphorescence was triplet to singlet, and from singlet to triplet it was going to be intersystem crossing, Then after coming to triplet, the emitted radiation was in the form of phosphorescence when it was returning to the singlet state. So in the intersystem crossing is singlet to triplet. Then we discuss the time scales. That for the absorption, it is 10 to minus 15 seconds. And fluorescence, it's minus 9, 10 minus 9 to 10 minus 7 seconds. Phosphorescence, it's 10 minus 3 to 10 raised to 2 seconds. This all you have to remember. Vibration relaxation also, it's 10 minus 14 to 10 raised to minus 11 seconds. Then we discuss what are quantum waves. So quantum wave is number of photons emitted to number of photons absorbed. That is emissive rate of fluorescence divided by emissive rate of fluorescence plus non-emissive rate. And in non-emissive rate it can be internal conversion, intersystem crossing, phosphorescence, and others that are not fluorescence. And in fluorescence lifetime, it is the mean time spent in the excited state before returning to the ground state. So for the fluorescence lifetime, it's 1 by emissive rate of fluorescence. Then we discuss about quenching. What's quenching? It is decrease in the fluorescence intensity, and it may occur due to collisional quenching, chemical quenching, static quenching, and concentration quenching. So basically, collisional quenching occurs in the excited state fluorescent molecule of the quencher, and there is interaction between these two. Static quenching occurs when there is complex formation in the ground state fluorescent molecule in the quencher, so it occurs in the ground state. Concentration quenching, if the concentration of the analyte is higher, then intensity can decrease. So basically it's a self-quenching. Chemical quenching may occur due to the change in pH, due to presence of dissolved oxygen, or due to heavy metals. And because of these, quenching can occur. A general example of quencher is chloride ions in case of quinine, as quinine is fluorescent, but if we add chloride in the quinine molecule, then the fluorescence is quenched. Then we discuss about energy transfer. That energy transfer can occur through post-resonance energy transfer. Basically, the FRAT is a non-radiative transition. It's a non-radiative transition. It occurs through long-range dipole-dipole interactions. Dipole-dipole interactions. And there are various prerequisites that must be met so that we can achieve the FRAT. Firstly, there should be spectral overlap. What do we mean by spectral overlap? That the donor emission should overlap with the receptor's absorption. Second, the orientation of the dipole should be optimum, and the best orientation is when they are parallel. Third, the distance between the donor and receptor. So these all things we have to keep in mind. Secondly, the energy transfer efficiency corresponds to 1 by R6 dependence. This is like from here, that's the graph is like that. It is inversely proportional to the R6 value. That's why the graph is like this. Then solve some question related to quantum and fluorescence lifetime. So if in this, what was the natural lifetime? It was the lifetime divided by the quantum mean. Then which will show intense fluorescence. We know that for a molecule to be fluorophore, it should be rigid. Therefore, there should be delocalization of the electrons. short excited lifetime. So all this corresponds to the characteristics of the fluorophore. Then we know that in the Stock shift, energy of the absorption is more than the energy of the emission. Therefore, for the emission, the wavelength is longer or larger. Emission is higher. The Stock shift. Then as eosine is more rigid, therefore phenolphthalein does not fluoresce. Then due to dissolved oxygen, like fluorescence intensity decreases in case of dissolved oxygen. Then just remember that out of fluorescence and absorption, fluorescence instrument is more sensitive. Why? Because every molecule that absorbs in UV can show fluorescence. Because it was like, except every molecule that absorbs in UV can show fluorescence. Because of that, fluorescence is sensitive. And then phosphorescence, it results from intersystem crossing. Then why in naphthalene the quantum it was higher, as the energy gap was maximum, so there was not good overlap between the wave functions, and due to that the internal conversion was low and quantum it was high. Then as fluorine is more rigid, so quantum efficiency is higher. Since all these molecules have heavy atom effect, like because of fluorine, chlorine, bromine, intensity decreases, but due to the size of bromine, as it is more, so intensity will be high in case of fluorescence. Then we discuss for Indian and trans-Stilbene. As in Stilbene, there can be rotation possible across the double bond. Therefore, quantum yield is less, while in first molecule, the indium, it's rigid, so quantum yield is more. But in Stilbene, it further increases. Why? Because at 77 Kelvin, it is frozen at the cooling state. Therefore, the rotations are like there will be no rotations, so it can't rotate. Therefore, the quantum yield increases because internal conversion decreases. Then we discuss why absorption and emission structure are the mirror image. Because the spacing between the vibrational levels are the same in the ground state and excited state, and when a molecule is in excited state, it may return to any of the vibration level of the ground state. Therefore, as a consequence, they appear as a mirror image. And this was due to the Stock shift we already discussed. Then you have to memorize these formulas, that energy transfer efficiency is inversely to the R6, that is R06 by R06 plus R6, where R0 is the posterior radius, R is the equilibrium separation, and for the energy rate transfer rate constant, it's 1 by tau d. Tau is the lifetime of the donor. So this all you have to remember. That's all for today. Is there any doubts? You may ask. So is there any doubts? Kartikeya, Rohit, Arun?
Ma'am,
Yeah.
what is the possible J values for the 4F, madam?
What will the possible
J values.
J values for?
4F, madam.
So for 4F.
Yes, madam. Yes.
So you know, J value, it can range from L plus S to L minus S.
Yes.
I think we have discussed this same question. the previous session.
Okay.
Yes, ma'am. We have discussed this question.
Yeah, it's already given. Like I think we have discussed 2 times maybe. So
Yes.
yeah, 4f. So here, what does 4 indicates?
Yes, madam. 2s plus 1 is
Yes.
equal to 4, madam. S is equal to 1.
Correct. 2s plus 1 is 4. And it's f. So it's S, P, D, F. So for L value for S it's 0, for P it's 1,
0.
D is 2, and F is 3. So L is 3. So from here you will get the value of S, and from here you will get the value of L. So L plus S you can calculate, and L minus S. So for that, if suppose L plus S comes out to be like it's here, S will be equal to 3 by 2, as it's 2S will be equal to 4 minus 1, that is 3. So S will be 3 by 2 and L is 3. So L is 3 and S is 3 by 2. Similarly this. So the solve this and this.
Ma'am, screen is not visible, ma'am. Means one presentation is appear, ma'am.
Just a second. Now is it visible?
Yes, ma'am.
So you can calculate the J value accordingly.
Madam, here my doubt is we are getting S value and L value, but if J is L plus S or L minus S, how we will define, madam? I mean, sir.
No, like firstly, if they're asking about the possible terms, all the possible, so you have to write all the terms. Secondly, if they're not asking the possible terms, then if it is more than half filled, if it is less than half filled, then we know, no, like if it is more than half filled, then you use L plus S.
Uh,
If it is less than half filled, you use L
L
minus
plus
S.
S.
And if it is exactly half filled, you use
Yes, ma'am.
L is equal to S. Yes.
Yes, ma'am.
Any further doubts? Any further doubts? Shreya, Rohit, Kartikeya. So if there are no doubts, then I can stop sharing. So thank you.
Thank you, ma'am.